Hi, in this video we will learn how one can use Gauss-Jordan elimination to compute the inverse of an invertible square matrix. Well, note that this is the first method we know to compute. We will learn to compute the inverse of matrices of order bigger than 2. So 3 by 3 matrices, 4 by 4, and so on. So let me recall first that if we start with the square matrix, so if A is an n by n matrix, and then we know that A is invertible if and only if the reduced row echelon form of A is the identity matrix of order n. In other words, there is a sequence of elementary row operations that transform A to identity matrix. So that's the first fact. But on the other hand, we know that the elementary row operations, let's say the first elementary row operation in that sequence, if you apply it on A, the result can be written by product of an elementary matrix. Let me call it E1 times A. And if we apply the second elementary row operation in that sequence, this time this matrix, which is E1A, will be multiplied by another elementary matrix. And you continue working on this. Let's say there are k elementary row operations in that sequence that turns A to identity. So then the last one, if you continue, we'll see that will have this form, ek multiplied to ek minus 1 up to E1 times A, and we know that this is the identity matrix. But what we found here is that, you see, we found a matrix which is product of some elementary matrices, which when you multiply to A from the left, you get identity matrix. Since A is a square, A and B are square matrices, then you can show that AB is equal to identity, and as a result A is invertible as we started with, and then the inverse of A is B, which is product of these elementary matrices. Very nice. This is very nice theory, but how you can use this to compute the inverse? Well, the key point here is that, well, I can write B or A inverse as ek multiplied to ek minus 1 up to E1 times identity matrix. Identity matrix acts like 1. Yes, when you multiply two matrices from left or right, you get the same matrix back. Why is that important, seeing that point? Because we can start with identity. Instead of working with A and transforming to identity, I can start with identity and apply exactly same operations that I applied on A to get identity. So here, this would be E1A. Then you apply the first operation. Then the second operation, you get E2, E1 identity. And you apply all these operations, you will get ek up to E2, E1 times identity. And this is what we are looking for. In other words, you have to keep track of all the steps you do, all the elementary row operation you do to turn A to identity, and then apply all those ones to identity matrix. Or easier way or a smarter way to do this is that you put A and I together in a matrix such that so you separate these guys with the lines so that they don't get combined, mixed. Now if you apply a row operation to A and apply it all the way through, automatically that operation will be applied on identity matrix. And this way, if your matrix is invertible, you will end up doing some works. You will end up with identity, turn A to identity, but identity will turn to your A inverse. This is the method or how Gauss-Jordan elimination works for computing inverse matrix. Gauss-Jordan elimination for computing inverse matrix. If I want to do this in steps, step 1 says that form this kind of augmented matrix AI. Put the right identity matrix which has the same number of rows as A. Then step 2, reduce it. Do the row or echelon find reduced row echelon form. So reduce it to reduced row echelon form. So you will get a matrix C and a D. Now, if what you got there on the right hand side here, if that guy C is the identity, in other words, the row echelon for reduced row echelon form of A is identity, then A is invertible. We already knew that. And as a result, A inverse is what you generated on the right hand side. In other words, you start with a I and do row echelon form, reduce it. If you get to identity, what you have on the other side of the line is A inverse. What if C is not identity? It means that, well, the row reduced echelon form of A is not identity. That means A is not invertible, and you don't need to be worried about the inverse of that matrix. So this, before I start doing some examples, let me just put one remark. The remark is that this method works not only for matrices with entries, real entries, but also works for matrices with entries in Zn. So this method works also for matrices with entries from modular integers Zn. So that not only we will find the inverse of matrices of higher order, but we can also use this method to find inverse of matrices from Zn or on Zn and so on. Okay, so let's do some examples. Okay, I have 3 examples here. So find the inverse if A is invertible. So we start always with A, 1, 0, 1, 0, 1, negative 1, 2, 1, 2. And on the right hand side, you put the identity matrix. Which identity matrix? Here, 3 by 3 identity matrix, the same order as A. Then, well, this is good. We have to kill that 2 there. So R3 minus 2 are R1. This will give us 0. This will give us 1. This will give us 0. And this will give us negative 2, 0, 1. The rest stays the same. Then, well, we need to take that one as our next leading one. That's nice one. Then we get rid of that one there. So R1 minus R3 minus R2. So this will be 0. 1 minus 1 is 0. 0 minus negative 1 is 1. And negative 2. Negative 1 here. And then 1 there. Everything else is the same. Now this is the leading one. We have to get rid of these entries. So R1 minus R3. So this will give us 1, 0, 0. So 1 minus negative 2 is 3. 0 minus negative 1 is 1. And 0 minus 1 is negative 1. Here, then we can get rid of this guy by R2 plus R3. So this is 0, 1, 0, negative 2, 0, 1. And the last entry stays the same. This is nice. Now, we already said this is a reduced row echelon form. This is identity. That means that we started with AI. We ended up with I something. That something is A inverse. So we found A inverse here, which is 3, 1, negative 1, negative 2, 0, 1, negative 2, negative 1, 1. That's the A inverse. Well, for 4 by 4, okay, so we start with this guy. Let me just, this way it will be quicker. So I will do this. 1, 0, 0, 0. This is 4 by 4 matrix. And then, okay, very nice. This is nice. We have to get rid of these guys. And for that, you get R2 minus R1. So this will give us 0, 1, 1, negative 1. On the right-hand side, we will get negative 1, 1, 0, 0. To get rid of these two, we have row 3 minus 2 row 1. So this will give us 0, 4, 1, and negative 2. This is negative 2, 0, 1, 0. For this one, we have to do row 4 plus 2 row 1. This is a 0, then another 0, and 0, and 0 here. Then this is 2. This is 0, 0, 1. The first row stays the same. But you notice something here, that the last row on the left-hand side is 0. It means that no matter what kind of work we do, we are not going to get identity matrix here. So the row reduced echelon form of this A is not identity matrix. That means that A is not invertible. That easy. You just got a very strong tool, not only computes the A inverse, but also tells you when a matrix is invertible or not. Okay. This last example we will do for a matrix on Z4. Okay. Okay, so we start with a I. So I here is 2 by 2. Well, this is nice. We have to get rid of this one. So we are looking for a number that when you multiply to this, yes, to 1, and you add it to the other one, it will be 0 in Z4. What is that number? It's not 0, it's not 1, it's not 2, but if you put 3 there, this would do the job. So that is how we get rid of that one. R2 plus 3 R1. This is 0. Then 2 times 3 is 6 plus 3 is 9. 9 in Z4 is the same thing as a 1. And on the right hand side you get 3 and 1. 1, 2, 1, 0. Okay, how about now? So this is nice. We have to get rid of this one. So we are looking for a number that when you multiply to 1 and then add it to 2, you get 0 in Z4. Yes, this we want to be 0. So here we have 0, 1, 2, 3. Apply one by one. For 0 won't work, 1 won't work, but for 2, yes, it is 2. So that's what you put here. So row 1 plus 2 row 2 is how you will get rid of that one. 3 times 2 is 6. 6 in Z4 is 2 plus 1 is 3. And this is 2. And this is 0, 1, 3, 1. Very nice. This is identity. So we started from AI. We ended up by AI something. That something is the inverse. A inverse is 3, 3, 2, 1. Note that if you've done this thing for 1, 2, 1, 3 in R, that you will get a completely different result in this case. Okay, so this is the technique you need to learn and use it when you need to compute inverse of a matrix.